All right, here in example 3, we kind of have an interesting question. We want to evaluate the following iterated integral, which is already kind of set up, but we would like to change it to cylindrical coordinates, because maybe right now we're looking at those bounds and that function and we're going, gosh, that looks annoying. Maybe we could change this to be something with cylindrical coordinates. Now, a big note here that I've left that's super important is that a lot of times when people first see this question, they start to just get a little bit antsy and they start just trying to like replace everything as fast as they can. But that's actually a really bad strategy. You don't just want to go through and replace every x with an r cosine and every y with an r sine. That's not necessarily the most helpful thing to do. So I want to try to go ahead and think carefully about how I convert each individual piece and then think about the region that I'm actually working with. Because without that, I'm going to kind of run into some trouble. Okay, so here's where I'm going to start. I'll start with this. I'm going to note that the function here that we're integrating seems to just have the formula of root x squared plus y squared. Now, of course, I can see that if I was working in cylindrical coordinates, that I can change this. So if I was to change this over into r cosine thetas and r sine thetas, again, if I converted this to polar, this should just be the square root of an r squared, also just known as an r. I don't have to worry about absolute value here because r is always treated here as a positive value. Okay, so, this kind of makes things look pretty nice. Notice that now I could start to think about the region that I've been given and how I could start to change some of the bounds. I'll state this. We see that E is given as a bunch of points, x comma y comma z, with the following bounds. Z's are bounded between 0 and 9 minus x squared minus y squared. Y's are bounded between 0 and 9 minus x squareds. And x's are bounded from -3 to +3. Again, I can't just go through and replace all of my stuff now with r cosines and r sines. I got to think a bit more carefully. Some of this stuff I can replace, and other things maybe not. I'll start with the bounds on z. Let's take a look. So if it's the case that z is bounded between these values here, then it seems perfectly obvious that z would also then be bounded between 0 and 9 minus r squared, since again, x squared minus y squared, or negative x squared minus y squared, should just be negative r squared. Okay, so I have bounds on z. But the weird part is to think about the projection into the xy plane. So when E is projected into the xy plane, we get D, which is a bunch of x comma y points where we can see where y is bounded and we can see where x is bounded. I'm just copying all of this from what we had before. But if I try to draw this region, I'm going to notice something. Notice the shape of this region, and then I'll figure out how to turn that into polar. So if x goes from -3 to +3, but y only goes from 0 up to this square root thing, any idea what this blue underlined portion could possibly be representing? Well, you might be able to guess that it's like sort of like the equation of a circle. Imagine here if I had something like y equals square root 9 minus x squared, that would give me y squared is equal to 9 minus x squared. And if I added the x squared to the other side, I have a circle. The only issue here is that I don't have both the positive and the negative portions for y. So what I really have here is only the top portion of a circle. This here is my region of D. So this makes it very interesting to see how I can re-express D. D could be considered as a polar region. And what would the bounds on R be? If you said 0 to 3, you're correct. What about the bounds on theta? Think about where you'd have to start looking and where you'd stop to visualize or to view all the values or all the spots. You'd have to start at 0, and I could go all the way to pi. So this gives me the ability to change the integral. So the integral that went -3 to 3, 0 to square root 9 minus x squared, and then 9 minus x squared minus y squared, and 0. I now have the ability to rewrite with polar coordinates. We know that if we integrate with theta last, I should have 0 to pi, r, 0 to 3. My z bounds were 0 to 9 minus r squared. My function, we said, changed to r, and then I had dz, and then my extra r in there, d theta. Again, that dy dx is going to need to be replaced by an r dr d theta. So from here, we could go ahead and actually work through this to see what we come up with. I'm going to ask you to try to go ahead and take a look at it, and then of course, pause the video, check back in a moment to see what you come up, to see if we got the same answer. All right, so the answer that I ended up with was 162 pi's over 5. If you'd like to check the solution up online, you can see all the work for that. Okay. Notice that we would have gotten the same answer here if we had stayed evaluating in rectangular, but you could just start to imagine how unbelievably messy that's going to look. Here you got to integrate things like, simple polynomials, and here you had to integrate crazy square roots, and it gets really ugly really fast. Okay, this concludes this particular section. I would highly recommend that you go and you take a look at a lot of the textbook problems from 4.5 and this first portion of 4.6. And in the next video, we'll start taking a look at 4.6.2.